Assalamualaikum. My name is Nurul Nadia binti Muhammad Sanusi. My matric number is 2022822188. Today I would like to present my final year project of a linear MHD flow of ternary hybrid over a vertical plate with viscous dissipation and radiation effects. For the first one is research backgrounds. Nanofluid are liquid with tiny particles, for the example Al2O3 and Cu. For the example Al2O3, Cu and Ag. The improvement heat transfer magnetic field effect nanofluid movement study using the finite element method FEM by Kumar et al. 2021, and then hybrid nanofluid two type of particle for better performance like CuOAg by Gumber et al. 2022, and ternary hybrid nanofluid use three type of particle for even more efficiency by Patai et al. 2024 and Isha et al. 2024. For the viscous dissipations, create heat but a heat sinks and suctions help cool the fluids by Chelili et al. 2023 and Lutera et al. 2024. And then for the thermal radiations, increase temperatures and fluid movement, improving heat transfer by Krishna et al. 2021 and Gambar et al. 2022. Three of problem statement. For the first one is heat transfer in industrial system using nanofluid magnetic fields is challenging because magnetic force can slow fluid movement, causing uneven temperature distributions by Kumar et al. 2021 and Rajas et al. 2021. And the second is hybrid and ternary hybrid nanofluids improve heat transfer, but their behavior under viscous dissipation and radiations effect not fully understood by Wahid et al. 2022 and Patai et al. 2024. And lastly, magnetohydrodynamic nanofluid face challenge in industrial due to magnetic force transfer efficiency, requiring further research to develop better cooling and heat transfer system by Ishaq et al. 2024. Research objective. Firstly, is study ternary hybrid nanofluid over a vertical plate with viscous dissipations, radiation effects. And second is develop equation for continuity, momentum, and energy in boundary layer flow. For the third is solve for velocity, temperature, skin frictions, and heat transfer coefficients using numerical method. And lastly, analyze the impact of magnetic field, nanoparticle volume frictions, Grosov number, and convections and radiation of flow and heat transfers. For the significance of study, improve cooling system, ternary hybrid nanofluid flow over a plate with a magnetic field, which can help improve cooling system in electronic and energy industry by Kumar et al. 2021 and Patai et al. 2024. And the next is effect of magnetic field and dissipations. Magnetic field and viscous or radiative dissipation change the fluid temperature and flow speed, affecting heat transfer. And then understanding heat transfer using math model and numerical method help us understand how things like nanoparticle, magnetic field, and radiation impact heat transfer by Chelili et al. 2023 and Lutera et al. 2024 and Isaac et al. 2024. The scope of study improve heat transfer. The study looked at ternary hybrid nanofluids on vertical plate to improve heat transfer with effect of magnetic field, viscous dissipations, and thermal radiations by Kumar et al. 2021 and Patai et al. 2024. And then better performance on ternary hybrid nanofluid than regular fluid. The study helped understand how this fluid affect temperature, velocity, and heat transfer by Kumar et al. 2021 and Patai et al. 2024. And then useful for cooling system. The study helped improve cooling system in electronic and other industry using nanofluid for better heat management by Gambar et al. 2022 and Muhammad Zukri et al. 2023. And then using numerical method, the study used numerical method like root quota method to analyze how magnetic field, viscous dissipation, and radiations affect heat transfer by Gambar et al. 2022 and Muhammad Zukri et al. 2023. For the viscous dissipation on vertical plate, viscous dissipations happen when fluid flow over a surface like a vertical plate, and frictions turn some of the fluid motions into heat, which rise the fluid temperature by Chelili et al. 2023. And then for the nanofluid are liquid with tiny particles like aluminium oxide or copper. These particles help the fluid transfer heat better, making it more efficient in systems where heat needs to be managed like cooling system by Aziz et al. 2020. Hybrid nanofluid are made by mixing two types of nanoparticles, which further improve the fluid's heat transfer abilities and handle extra heat caused by viscous dissipation by Land et al. 2023. For the ternary hybrid nanofluid, combine three types of nanoparticle offering the best heat transfer properties. They reduce energy. They can reduce energy loss and are even more effective in managed in complex systems by Goodry et al. 2022. Radiation on vertical plate nanofluid are liquid with tiny particles added to them, like copper or silver. When the fluid are exposed to radiation on a vertical plate, they heat up faster and move heat more efficiently by Comber et al. 2022. And then for the hybrid nanofluid, mix two different types of particles in the fluid. That radiation helps the fluid transfer heat better by making it hotter, which improves its performance in systems like cooling system by Comber et al. 2022. For the ternary hybrid nanofluids, which use three types of particles, are even better at transferring heat radiations, and these particles together help fluid get hotter and move heat faster by Patay et al. 2024. When magnetic field and radiation work together on this fluid over a vertical plate, they help changing the fluids by changing the fluid's speed and temperature, making them great for things like cooling system by Krishna et al. 2021. For the mixed convections or vertical plate, nanofluid can increase heat transfer efficiency, but too many particles can also cause more resistance in the flow by Patel and Kalkurni 2020. And then for the hybrid nanofluid, help improve thermal performance, especially in a system with magnetic fields and radiations. These fluids are good for cooling system and can manage heat more efficiently over vertical plate by Wahid et al. 2022. And then for the ternary hybrid nanofluids, show the best heat transfer performance with higher thermal conductivity and better thermophysical property. They can even more efficiency in mixed convection system. They work well with magnetic field and thermal radiations, increase the field temperature and heat transfer efficiency by Patay et al. 2024. For the numerical method, nanofluid method like Ruth-Cotta and Borgiorno model, which involve solving ordinary differential equation (ODE), help analyze heat transfer in nanofluid by considering how tiny particle and fluid movement affect the heat flow by Mustafa et al. 2040. And then for the hybrid nanofluid using ODE and MATLAB, which show how particle concentrations, magnetic fields, and radiation influence heat transfer efficiency by Wahid et al. 2022. For the ternary hybrid nanofluid are studied with ODE and the Laplace transform method show magnetic fields slow down the fluid flow by Patay et al. 2024. Formulation of mathematical model. For the first one is look at how ternary hybrid nanofluid, silver, copper, aluminum in water flow on a vertical plate under a magnetic field, heat radiation and frictions. And for the second is use math equation to study mass, momentum and heat transfer in the fluid. And for the third is make equations easier by turning them into simpler ordinary differential equations (ODE). And the fourth is solve the equations using computer method to find how fluid speed and temperature change. And the last, magnetic field slow the fluid but rise the temperature, radiation help heat transfers, and viscous dissipation create extra heat. Ternary hybrid nanofluid are good for cooling system. For the 2D boundary layer, magnetic field for the B naught represent the strength of applied magnetic field, and for the coordinate system X and Y define the reference plane on the vertical plate. For the thermal equilibrium, assume no sliding between the base fluid and nanoparticle, ensure the thermal balance. For the ternary hybrid nanofluid, we use silver, copper, and alumina and nanoparticle to improve thermal efficiency and fluid flow. And then for the viscous dissipation and radiations, heat transfer via electromagnetic wave, important for the described momentum boundary layer and advanced heat transfer system. Algorithm governing equation for fluid dynamics, non-dimensionless partial differential equations, simulate MHD flow of a ternary hybrid nanofluid over a vertical plate with dissipations and radiations effect, continuity equations, ensure mass conservations, momentum equation, account for magnetic field and beyond force, energy equations describe heat transfer affected by dissipations and radiations, effect on magnetic fields, influence fluid motions. For the viscous dissipations, generate heat due to internal frictions, radiations transfer heat through the electromagnetic wave. This factor affect velocity temperature distributions, and and the thermal boundary layer, improving flow of heat transfer analysis. There are algorithms governing equation of fluid dynamics, non-dimensionless partial differential equation, and similarity transformations. They show a governing equation for fluid dynamic dimensionless ordinary differentials, equation implementation of algorithm purpose, and the table of thermophysical properties of base fluid and hybrid nanofluid. For the numerical method, examines the effects of magnetohydrodynamic and thermal radiation on ternary hybrid nanofluids over a vertical plate. Use aluminium oxides, copper, and silver in water as a base fluids. For the mathematical model, governing equation momentum are converted into ordinary differential equations. Boundary conditions are set for magnetohydrodynamic flow with viscous dissipation and radiation effects. Numerical solutions (ODE) are solved using the fourth-order Root-Kotta method in Maple software. For the magnetic field, reduce velocity but increase temperatures and concentrations profile. Radiation parameter outside the effect increase velocity, decrease temperatures. Spherical nanoparticle lower skin frictions, better heat transfer efficiency. For the engineering applications, use in cooling system, energy device, and advanced heat transfer applications.